Hi everyone. So, today I wanted to talk to you about fun with bit hacks in C Sharp and what to do with them in sort of like interesting ways and how they're like related to data and design and performance. And we're gonna look at some interesting examples hopefully. So let's jump in. So, if we want to use like bit hacks or bit twinkling hacks as they're sometimes called, then we do it for a couple of reasons, like usually most of the time, right? So one of the interesting reasons why would you ever want to do like bit manipulation as opposed to just doing like some simple stuff, because I'm just talking about like much more advanced stuff than just doing like and ors and stuff like that. Well, one of the things that you want them to use for is to do branch elimination. Another interesting reason is batch computation on like entire processor words. And yet another interesting example, interesting use case is if you want to have like a more compact or compressed representation of your data. So there's a couple of like data structures that actually allows us to represent a huge amount of data using just a small bit mask, which is interesting. And lastly, we can do it for simplicity because sometimes it just makes sense. So today we're actually going to be talking about the first two, but let's actually briefly talk about the last two. Without any examples, let me just give you some like proper context on and like just tiny examples of why would you want them to use them for this sort of purpose. So for simplicity, let's just say that you have a small permission system with like a role system implemented on top of that. You could use an int32 in your database and use bits to represent different roles. And that's one of the simplest ways how you could sort of expose, like not expose, but use that bit manipulations. And let's just say now that the problem gets complicated, and instead of like a row system, you also have like a granular permission system. So what you can do in order to expand this idea, you could, for example, create a matrix. So a bunch of these N32s, like or perhaps use an array, and that's gonna be it, right? And you can implement your role systems on top of your like permission systems on top of your role system, and that's gonna be good. Especially it's good because people most of the time people will just reject this idea, but if you get comfortable with using like bit manipulations, you're gonna see that this idea is actually really good. Yeah, so point number 3, compact data representation. So what we have, sometimes we want to represent sets and we want to sort of say that a value is within a certain set. We can use a bit mask for that. It's very cheap. Checking is very inexpensive. Adding bits to a bit mask is really inexpensive as well. Processors can do it really efficiently today, so that's not a problem. That's going to be very quick. And on top of that, most of these sort of bitmaps will have a bunch of ones and a lot of zeros, so you can do like run length encoding to compress them. And there's a bunch of like data structures that do compression on bitmaps, and that's going to be a very compact data representation. Another thing that we can use them for is, for example, like probabilistic data structures, which are really interesting because they're going to represent huge data sets with just small bit masks, but they will give you a probability of false positives, and you can handle that. Certain databases, actually nowadays most databases use, especially the newer ones, certain probabilistic data structures because of the volume that you have to do. It's often really good to just have a probability of a occurrence or like a count of a set than like full specific count, because that's going to be expensive. And one of these data structures that are used very commonly today is a Bloom filter. Another one is called a hyperlog or hyperloglog, which is like just distinct count data structure. But we're not gonna talk about them today. I'm planning different videos on these subjects because I have like a lot of things. So the next thing is batch computation, and it's like a worldwide batch computation. So processors actually read and write stuff in units of data called words. They're usually 64 bits, which is 8 bytes. So if we have data that's actually less than 64 bits, and we can pack a bunch of these values in a single word, then we're gonna do stuff in batches. It gets even better if we use things like SIMD instructions, which means single instruction, multiple data. Then we can actually pack a lot of words, so it's gonna be like a big vector, and that's gonna be even quicker. So that's really good. And lastly, the thing that I'm gonna talk about today on this video most of the time is gonna be branch elimination. So each time you have an if statement in your code, it actually gets the compiler will actually emit what we call a compare instruction, which is a test, and a jump instruction, which is the branch. So this is how your if statement is most of the time implemented. And that's all good, but these jumps are usually expensive to do. Well, they're inexpensive, but they're expensive because you have to jump. So what will happen is that modern processors will actually do a predictive analysis, and they will try to guess if you're gonna actually jump multiple times. And they're gonna actually take these instructions from that jump and put it into their pipeline. So in order to not just, because we don't want to stall the pipeline for like a lot of time, we're gonna actually try and guess. And there is like a branch prediction table, and it's like all good. There's a lot of like different components that actually make this hardware component work. The most interesting thing about this is that if you have a branch misprediction, so processor will like try to guess, it will fail to guess, and the pipeline is actually pretty long. Modern like CPU architectures have long pipelines. Then at some point there's going to be a checkpoint, and we're going to determine if that our assumption was correct, and if it isn't, we have to throw away this entire like pipeline and start again, which is very expensive. So what you want to do most of the time is to not have to pay that cost if you don't need it. And we're going to look at some examples how we can deal with that, because that sometimes in like most of the systems, people don't actually pay a lot of attention to branches, and sometimes they will just max out performance of their like algorithm and data structure because they don't actually know that you can do branch elimination most of the time, or it's really hard to do, and you have to use these bit hacks that are really difficult to like create and find sometimes on the web or create yourself. But hopefully we're gonna see that it's to start with, it's not that difficult, and once your like knowledge expands about this topic, it's gonna be even better. Okay, let's jump into some code. So let's look at this very simple example for now, where what we just want to do is we want to count even numbers. So we're gonna get an array of numbers, and if the number is even, we're gonna increment the counter. So that's like the simplest thing that you can have here. And we're just gonna run it and measure the execution time. So what I did here is I have like a simple measuring function which has a warm-up phase, and it's gonna do stuff a lot of times, right, and measure performance. So, just a bit about testing these sort of operations. So, it's really difficult to test since, like I said, the processor has a really sophisticated branch prediction algorithms inside. So, if you're just gonna have like simple increasing sequence, for example, it's gonna guess that correctly. So if you have like a warm-up phase, which you should have because certain things are not compiled yet, not optimized yet, so we're gonna have a cold start problem. It will absolutely guess your branches, and you will not measure the thing that you wanted to measure. So in order to actually see if this behaves correctly, what we have to do is we have to generate these like random numbers. So we're going to have a random here. We're going to do random next, and we're going to add something extra, which is like milliseconds to the equation, and that's going to be it. So let's see how our like simple version performs. Let's compile. And our simple version performs in 28 milliseconds. Seems good, seems reasonable. Let's actually see now how can we improve upon this thing. So how would we do better in this example? Can we actually do better? Well, as it turns out, we can indeed do better. So we can actually eliminate this branch here. How? Well, if we wanted to count like even numbers, or actually odd numbers, a significant bit will tell us that a number is like odd or even. So what we have to do is we have to actually do an AND operation. And that will actually give us if the number is odd. So if the number is odd, then we're going to have a 1 here, which is true. And if it's even, it's going to be 0. So what we have to do in order to like flip this around to even numbers, if we have to have this sort of small equation here where we have 1 minus add. So like I said, if the number is even, there's going to be 1 here. So 1 minus 1 equals 0. And if we have an even number, there's going to be 0 here. So we're going to increment the counter by 1. Okay, let's measure the performance of this branch tree version. 25 milliseconds. So let's just compare how these two stack against each other. 44 to 25. Okay, we can see that we have already an improvement here. However, the question is, can we do better? And as it turns out, yes, we indeed can do better. Because this operation is actually not that really, it's not really expensive, but we can still optimize it and get rid of this operation here. So since we know like the size of our array, and we know how to efficiently calculate odd numbers, really, what we can do is we can actually just count odd numbers and then subtract them from the numbers, which will give us all of the even numbers. And in this example, this is what we're actually doing. So we're actually calculating odd numbers, and we're actually at the end, we're just going to subtract. So let's measure the performance of this guy. 14 milliseconds as compared to like what, 25, right? Yep. So we did better. Question is, can we do even better? And the answer is, of course we can. It's still not the best version. It's the most like clean and understandable version, but if we wanted to go really fast, we can still do better. So how do we do better? Well, we can actually do SIMD instructions. So like I said, SIMD is single instruction multiple data. And what we're going to have here is we're going to actually do an operation on a vector. So right now we're actually going slightly to point 2, which is actually we're gonna do batch operations. So we can actually load up 4 integers from that array and we can do an AND operation as we did here. We're gonna do the same thing. Then we're gonna add that to our like counter here. And what we're gonna end up with is actually not a single counter, but 4 counters. So now we have to horizontally add them together. So it's like we're gonna add 2 and 2 and 2 and 2, which is actually 4. We're gonna return a scalar, which is a single value, and we're gonna have our odd counter, not even counter. So the things that actually couldn't be nicely packed into blocks, we have to do manually here. But that's fine because that's just a reminder. So once we have that, we do our operation. We're gonna subtract that from the we're gonna subtract the odd count from like the total of our array, which will leave us with the even count. And let's see how that performs. 4 milliseconds. So we started up with 30-ish milliseconds, right? 30, 47 actually, it depends. Then we went to 22 to actually 16, and now we're at 4 to 3. We're actually at 4. That's a pretty good improvement. So hopefully you see that branch elimination is worth it. This is just a simple branch because I didn't want to get into like very complicated ones, but the more branches you have, the more nested and wide branches. So if, else if you have, then your results should be even better. Of course, it's really tough to eliminate such complex branches, but you can do it one step at a time. So this was a simple example. Let's actually look at a more complicated example. So let's just say that we have a function here that will take some string and it will try to find and count a character within that string. So again, this is our simplest implementation here. So it's like, very simple, nothing really special happens here. Let's just say that we're interested in like finding white space. So let's just uncomment this one. So we're just gonna count a white space. Let's create our text, and again, it's sort of like random. It has to be a bit random, so we're gonna just use the random next to string, and we're gonna just add the I here, and that's it. And we're gonna add a space. So this will actually end up in a lot of like spaces, and since it's increasing, the sequence is increasing, there's gonna be less and less spaces, and that's not actually pretty good to test. But for now, let's just say it's sufficient. And okay. Let's see how it performs. All right. So we don't have a reference, so let's just take that as it is, and let's ask the question: can we actually do better? And the question and the answer is probably somewhat surprising, because yeah, we can, but this is actually much more difficult than it sounds. So there's a couple of ideas that we sort of can have. Let's start with the simplest one. So let's use our like entire processor word to be able to actually do that. And let's see how we can actually eliminate this branch here as well. So what we're trying to do in this example here, in this function, we're trying to do batch operations. So we're trying to do a couple of things at the same time. And on top of that, we have to somehow eliminate this branch. So we're actually using a function called between here. And this will actually tell us if a character is between any two characters, like a range, and this is like exclusive. So if we're looking, for example, for the white space, which is 32, in like byte values, then we have to have stuff. We're gonna look for stuff like from 31 to 33. And how this actually is implemented is this very like complicated function, which uses a function called has between, and this is our like bit hack, which actually is capable of counting stuff between these two things. There's a couple of like gotchas here. So this actually goes from 0 to 127, and this as well goes to 0 to 137, because they cannot actually go above 255. So yeah, sorry, actually that's not correct really. So this is from 0 to 127. This is from 0 to 127. Now why is that? To 127. Why is that really? It's just how this function is really implemented. You could actually have a better one, but it would do actually much more of these operations, and it would be actually slower. So for the majority of cases, this is all that we need. So we're not going to come up with a more difficult one, but we still have to count, and this small operation will actually allows us to count how many of these bytes we actually have in a processor word here. So let's actually try and run it, because this is like 300-ish milliseconds, and let's see how this performs. It's actually slower. And why is that? So we've actually been able to eliminate our branch. But the problem here is that this is so extremely complicated that it doesn't help a lot really. And since this gets called a lot of times, and it's gonna like slow us down. So not all bit hacks are like good in all like a lot of contexts. This has an application, but this application is actually better if you like break the chain. So you have not a big amount of white spaces in your text most of the time, but we can. So the question actually now is, can we do better? Because this is actually slower. We don't want it to be slower. We actually want it to go faster, not slower. And especially we want it to go faster because we're now having to deal with all of these complexities in this function. And remember, this used to be like a really simple thing, right? So it's not very good. So how to deal with this? Well, there's a way. And but before we get into how to deal with this, let's actually turn this around and let's actually do something different, which is actually much more simple. So we can have a function like that. So this will just eliminate the branch. And how does it eliminate this branch, right? So it's a simple function. It actually uses one character at a time, but it will not have any branches. So since we're interested in like finding a white space, we can have something that we call a jump table, and the jump table will actually contain a table of stuff. So let's actually do some typing here. So we know that our white space character is actually 42. So our jump table will be so the value of this white space will be the index of the jump table at position 32. So we're gonna actually do this, and then under that index we're gonna have stuff that's called 1, and under every single other index like 33 and stuff like that, we're gonna have 0. So what we're gonna end up with here is that each time we see a white space, we're gonna hit a 1. Otherwise, we're gonna hit a 0. And this is implemented as a table because we can actually have multiple things that we can look for, not just like single characters. Now we can have multiples of characters. And the jump table is actually allowing that to happen. So let's modify our code and let's run the jump table example. And we have to initialize the table first, and let's see how it performs. Still, let's actually run it again. Okay, because we did a lot of branch predictions and it got our pattern. So 350 milliseconds. It's not like great, not terrible. Let's actually see how we did perform with just simple function counting. It's like more or less the same. I would say, yeah. So the jump table is actually more performant. Yep, it's more performant than just a count. So actually, our branch prediction elimination worked in this example, but we would still want to do stuff on like the entire words of a processor, right? So how would we do that? So we can come up with a different function that's called count compact. We could actually use that array here as well, but we're not gonna for this example. And what we're gonna do here is we're gonna have the same function as we did before, but we're gonna change one thing. So we're gonna check if our entire word has a single white space in it. And if it has, then we're gonna count the instances of this white space, but if it hasn't, then we're just gonna move on. And how this is implemented. So this is implemented as using has 0 bytes. This is just a XOR operation. And people actually, this is really interesting historically because people actually a long time ago came up with this equation here. And it was actually, I believe, explored using like some algorithms to be able to find this set of magic numbers. And a lot of like bit hacks uses this formula because it's most of the time you're interested if you have a 0 byte somewhere in your code, in your like value, and instead of in the cases of text, we actually have that because, well, surprise, surprise, dotnet text is based on Unicode, so we have either 2 or 4 bytes. So if we're not gonna have like fancy characters beyond ASCII, for example, if we're not gonna have beyond ASCII characters, then one of the bytes is always empty, so it's a 0 byte. So that's useful, even for this. But there's like you can use this 0 byte to actually determine if you have a value in your like big word. So this is the trick. I'm not gonna do a lot of explanations on this. You can read the full like detailed explanation here. This is a book where a lot of these things are like sort of implemented. There's multiple approaches, and it's a really good book. It's free, so you can use this as a learning tool for now. Alright, so let's actually look how the compact version performs. It is better, but it's not really better from like the simple version. And why is that? Well, the reason is because now we're paying the cost of that branch. So we could actually optimize this, but I'm not gonna do it for now. But still, even if we optimize this branch away, we still have a problem where we still have to do this expensive count between operation. And this is largely dependent on the dataset that we have. So if we have a dataset where there's a few of the things that we're looking for, like white space, for example, there's just a couple of white space in a big string, then it's going to perform really fast. But if there's a lot of white spaces, it's going to be slower than your like simple method of counting characters, or your a bit better like jump table example. We can of course still do better using SIMD instructions, but this time around I'm not going to show you that because there's a lot of operations that have to go into the SIMD instructions, and the code is really big and hard to follow, so I guess I'm just gonna leave that out. But in reality, that jump table for this example is actually better because it is faster, it eliminates the branch, and it's easy to understand. But still, we can do better if we have some context. So let's just say for now that all that we want to do is that we want to find not any like character, but a specific character which is a white space. And if we know that we have a problem like that, where for example we need to split stuff by words, and that thing that splits them is the white space, then what we can actually do, knowing that, we can actually implement a different operation based on the same like word algorithm, right? So it's not this one, it's this one. We can have a different kind of function which is called countless, and I'm gonna try to explain this as best as I can. So countless is a function which actually says that I'm gonna find a byte. So I'm gonna count how many times a word contains a byte that it's less than this n here. So if we say that our white space is 32, if we're gonna say that countless 33, so count the stuff that actually is less than 33, which is I believe a character. We're gonna end up with a pretty good counts of white spaces and unfortunately all other stuff which is less than 32. But most of the time 32 is white space, and below white space there aren't really characters that we care about because there are like control codes and stuff like that. So that's all good, right? Well, not exactly, because like I said, UTF-8 has 2 bytes, and if we're gonna have a ASCII range, one of the bytes is gonna be always 0, and that's gonna get counted as well. So that's a problem, because we're gonna do double counting most of the time. Or actually not even double counting, but we're gonna count more stuff than we should. So how would we deal with this? Well, let's just count all of the stuff that is less than a, so it's white space and or other like characters, control codes, 0 bytes and stuff. And then that if we know that we have a UTF-8 all ASCII, then what we can do here is we can subtract. So we take all of our characters and we subtract them from the count, because we count, what we're actually doing is we're counting each character, and then we're counting white spaces as well. So we have to subtract that from the counter, and we're just gonna get white space, which is really good. And of course, this is like a simple example. If you wanted to do like non-ASCII characters, that would be slightly more complicated, not much really complicated. The complication actually begins if we're trying to move from like 2 bytes to 4 bytes of Unicode characters, but it's still doable. I'm not going to show you this example now because it's much more code, and this is already confusing in a way. All right. But let's check how this performs. It actually performs pretty awesome, because let's compare it to this version. So this is actually really good, 2 times faster. Can we do better? Yes, we can. We can do our compaction algorithm where we first check if we have the value and then we're going to count less. That's one of the ways, and of course we can do SIMD instructions as well. We can do a jump table as well, but for now, again, let's leave these alone. Let's just concentrate on this example because it's way less code, right? So let's measure this. Whoops. Well, it didn't perform, right? Why is that? Well, like I said, we have a branch here, which is not really all that good. And we have this check, but this check is really inexpensive. But this is expensive. So in order to actually make this happen, we would have to resort to a jump table here. And that would be on par and probably faster. But like I said, I'm not going to show you that now, because like I said, maybe I'm going to do it in a different video, not this one. All right, so that's all that I wanted to show you this time around. There's gonna be more videos like that coming because there's a lot of like things that we can do with bit operations, especially data structures and probabilistic data structures. And yeah, so that's all for now. That's all for this video. If leave a thumbs up if you enjoyed it, if you got something out of it, and hope that we're gonna see another one next time. Yeah. All right. So thanks. Bye.